Last time we played with composition pointers that organized our data structures in perfect trees, which ideally matches data structures of every nowadays application. But what if we need to handle links between those tree nodes? Real applications use links very heavily. In databases, foreign key relationships doesn't mean one table owns the other. In programming languages, AST nodes can freely reference variable and type declarations. In graphical user interfaces, different UI controls can reference one another, models and controllers. We can think of weak pointers as mirroring relationships represented by ID or href attributes in JSON or XML. All these examples show non-owning or weak association between objects. They are a type of connection that is portrayed in UML with links having no diamonds. In Argentum, we declare weak pointers using the ampersand prefix, like this. This expression creates a disconnected weak pointer. And this operator creates a weak pointer out of owning pointer types. Here, X owns the myClass instance, while W merely observes it. If X goes away, W automatically becomes disconnected. So in order to safely use weak pointers, we need to first check and protect their targets from being deleted. Argentum doesn't have any special syntax for that. Instead, it employs the already known question mark and colon operators, and this means we cannot skip checks, and we must provide some code path for the case ID link is lost. No crashes, as we like it. In this example, we check if W is bound and call some method on its target. In the previous chapter, we introduced a copy operator. It handles weak pointer in a very clever way. Imagine we have a data structure with internal interconnections. A graph object that holds a collection of nodes, each having a weak link to one other node. When we copy such a graph, the resulting graph perfectly retains all internal topology. This operation is performed without any memory and CPU overheads in the most optimized way. Argentum has weak array and weak map that allows one-to-many weak links. Let's recap. Argentum supports weak links natively, with no overheads and limitations. It doesn't allow access to the target without locks, thus guarding memory safety. It mandates checks, thus enforcing resilience. It does so using already well-known operators, keeping the program design simple. It has a very clever built-in copy operation, topology-aware, high-efficient, and always correct. What about memory leaks? Weak pointers don't retain objects. When locked, they produce leak-proof optional temporary pointers. So memory safety keeps on. In the next chapter, we'll look at the shared ownership.